Hi guys! Today we're going to be talking about classes of chemical reactions, and there's 5 different types of reactions that we're going to be looking at today. The first is a synthesis reaction, and that is when we have 2 elements coming together to form one compound. As you can see up here, our pattern for that is A plus B is going to yield A and B together, and the example would be hydrogen gas combining with oxygen gas to yield water vapor.
We have one element, and one compound formed.
Our second type of our class of reaction is decomposition. That is basically the opposite of synthesis. So that is when we have one compound breaking apart into 2 smaller products, okay? That can sometimes be 2 elements, sometimes that can be an element and a compound, but basically we have one reactant, 2 products. That is what our pattern is right here. One reactant together, breaking apart into 2 different products. Our example would be peroxide in the presence of manganese 4 oxide will break down into oxygen gas and water. You can see that this was an example where we had one compound and it broke down into one element and another compound. And I just want to remind you that manganese 4 oxide right there is a catalyst, so it needs to be included in our chemical reaction, but it's not actually forming any bonds or breaking any bonds, so that's why it hangs out up there above our yield sign, and it still exists at the end. It's basically, it's not written as a reactant or product, but it's at both the start and the end of the chemical reaction.
And it's just there to speed up the chemical reaction, to make it go faster. One thing, if you're trying to remember synthesis and decomposition, remember synthesis means to make something, so we're making one compound. Decomposing is to break something apart, right? Things decomposing in nature, they're breaking apart or they're breaking down. So we have a compound breaking down into 2 products.
Our third type or class of chemical reaction is a combustion reaction. Now we talked about this one at the beginning of the year when we did our burning candle lab, which you can see is actually our example. And it is when a hydrocarbon burns in the presence of oxygen to form carbon dioxide and water. Now, this is how every single combustion reaction works. This is probably the reaction that is very most important to our lives. This is not only how our bodies make energy, but also how this is what cellular respiration is, but it is also what the reaction that's happening in your car's engine to get you here to school, having the lights on, etc. So the clue for that is that oxygen gas is always a reactant. So you can see it's going to be on that left side of our chemical reaction, and our 2 products will always be carbon dioxide and water. Now, for these first 2 reactions, we're never going to have you predict what the product is going to be, but for this type, we will, because the product is only ever carbon dioxide and water every single time. It's just different amounts of it, which means you would just end up changing the coefficient at the front. And a hydrocarbon, remember, is just a molecule of carbon atoms and hydrogen atoms bonded together, usually in this long chain, and those bonds have a lot of energy in them. That's why there's a lot of energy released during this type of reaction. So our example we used from our burning candle lab is our paraffin wax, which as a gas burns in the presence of oxygen gas and breaks down into carbon dioxide and water vapor. You can see that this type of equation takes a little bit long time to balance, because there's one hydrocarbon uses up a lot of oxygen and produces a lot of carbon dioxide.
All right, our next 2 classes of reactions are called single replacement and double replacement reactions. They're a little bit longer, but they're pretty easy to figure out once you get the hang of it. Our pattern that we see here is A plus BX. That's an element plus a compound, yielding B plus AX. Now, this is called single replacement. The reason it's called single replacement is because we see A is coming in and kicking off B, which then ends up as a lone element by itself. So really what's happening is A is replacing B. So instead of BX, we now have AX. And B is going to be the lone element there. Our clue over there, if you look, is 1 element plus 1 compound will yield 1 element plus 1 compound. That's what we see here in our example. We have aluminum, our element, plus copper 2 chloride, our compound. is yielding copper, our element, and aluminum chloride, our compound. So what's happening is aluminum is coming in, kicking off the copper, which is then its own element. So aluminum is bonding with the chloride. Okay. Our last class of reaction, which we're going to look at closer in our lab that we're going to do, is a double replacement reaction. All right. So we had one replacement happening here. In double replacement, we have two replacements happening. A will kick out B. B will kick out A. So really, it's going to look like A and B are just switching places. So instead of AX and BY, our products are BX and AY. What you'll notice for this is that both of our reactants are always aqueous. They're two compounds, they're always aqueous. They're going to produce one aqueous product and one product that I have a question mark for. That's because it can either be a solid, a liquid, or a gas. Okay? So our clue over there in green for double replacement is we'll have two compounds that are both aqueous, producing two compounds. Okay? Our first example is a precipitate in an ionic salt reaction. Now, what is a precipitate? If we look over there to our little bubble, a precipitate is a solid that's formed in a liquid solution. All right, so sometimes this will look like a cloudy substance. Sometimes you'll actually be able to see in the bottom of a beaker little solid particles that are collecting in the liquid. Okay, so we're forming a precipitate, a solid, in ionic salt reaction. We have ionic salts coming together to produce, right, two compounds that are aqueous, to produce an aqueous compound and a solid compound, right? So silver chloride here is our solid that's formed. Ag kicks out K, potassium kicks out silver, okay? The second example we have is water being formed in an acid-base reaction, okay? So remember our acids start with H, they have hydrogen at the beginning, and they're aqueous. Here's my acid. It's a compound, it's aqueous. Here's my base, right? We know that because we see an OH, a hydroxide here. All right, so calcium hydroxide, aqueous, plus hydrochloric acid, aqueous, is going to form two products. One of them, calcium chloride, is aqueous. The other one, water, is our liquid. Up here we formed a solid, here we're forming a liquid. Now you see calcium is coming out and kicking out the H. That means calcium's bonding with chloride. The H, the hydrogen, is kicking out the calcium. So now we have H bonding with OH.
Which, yeah, so we're going to probably first write it as HOH maybe, and then you can adjust. You can see there's two hydrogens, one oxygen, that's water.
Right, so we're forming water there. That's our liquid. The last example, we've already formed a solid, we formed a liquid, now we're forming a gas. We have our two reactants, both compounds, both aqueous. Sodium is going to come in. It's going to kick out the hydrogen. Hydrogen is then going to kick out the sodium. And as a result, we have sodium sulfate formed. This is our aqueous product. We're always having one aqueous product. And our gaseous product, which is hydrogen cyanide. All right? So solid, liquid, gas formed in this last class of reaction.